yeah, as Onur said, today will be recitation, and I'm gonna go over like materials that we've been over in the class, and if you have any questions, feel free to ask them. And I'm gonna have like some practice questions for you guys to do later. And I plan to have like some bonus points for you guys for the homework. For the homework too, if you can answer some of these practice questions. And here's the upcoming schedule. Tonight by midnight, and we have some spare like slack time for you guys. So if you like have to submit say 5 minutes after midnight, say Comcast at your apartment decide to like went down something like that, should be okay. But the actual deadline will be like midnight and a little bit afterward. By Wednesday, homework 2 is due. Pretty much the same drill as homework 1, but be aware that it's a lot longer than homework 1. 15 pages long. If you haven't looked at it yet, please take a look and think about the question a little bit, so you have like, once you actually try to do the homework, it's like, oh, yeah, I think I saw this question like before when I read it. And exam 1 will be like in 1 month. And right now, like today, we are about a quarter through for the whole class, like 4 weeks of 16 weeks. And lab 1 feedback. I think most of the common errors would be on the like corner case of CPSR. We have a few people who had like bugs on the PC value. Say for example, some people forgot to add the PC value at the last, like very last cycle, so they lose points on that.
What do you mean the last cycle?
It's like every PC value is correct until the last cycle, and you do like SPY 10.
Well, why does it matter what the PC is when you do SPY 10?
Well, I mean,
because
right
you're
before
halting.
that, right before that instruction, like right before it actually exits the execution.
But then the value isn't defined for that instruction because...
No, I meant like the instruction before.
Like at SPY 10,
Yeah.
what is the address of SPY 10? Plus E. Or not plus E.
And the most common would be like, we have some weird instructions, and CPSR is different than our simulator. We are gonna release the set of tests that you guys fail within each of your panic directory, so you can see the name of the test that we are testing and you guys fail on, so that you know to be aware of that particular instruction for future labs.
When will that happen?
For today's lab.
Yeah, you can ask this guy. So when's the expected time that we're gonna parse the name of the test that these people fail on?
I'm assuming by Monday it should be out.
Okay, so it's not gonna be ready by lab 2, but hope that will help for lab 3.
We'll try to get it today, obviously.
Okay, yeah, because I was assuming this should be done before in the previous semester. So we are being a little bit more lenient on you guys, because ARM has a lot of like corner cases you can fail on, like all the condition codes and the PC values compared to MIPS. And for the homework one, there are some common mistakes, like you guys somehow count the bits wrong, like you did everything correct, like every instruction looks fine, multiply numbers, and the number is all like 9 multiplied by 3 becomes 24. And those are pretty common. I'm not sure why, but like please be careful with that. I don't like take a little bit of points off because of that, but because it's incorrect, I have to like one or 2 points off. On the data flow question, please make sure you have arrows. Don't just use lines, because I don't know what produce value to what. And also, if say this particular bubble should take 1 or 2 inputs, don't put 4 or 5 inputs into one like bubble, because I had a few people doing that. If that's the case, let's have multiple bubbles that take a value and then gets propagated to the next bubble. I mean the next stage in the data flow. And for the question on variable length encoding, a lot of people use a fixed number of bits for the opcode, say because we have 8 instructions. you use 3 bits for each of the instructions. One possible optimization, and actually Onur went over this a little bit in class on how Intel X86 done their variable encoding, is to use a Huffman encoding, because once you know which instruction is more commonly used, you can use fewer bits. It's like when you are compressing the data, so that in the end your code size is smaller than what it should have been. So one possible optimization is Huffman encoding for that. And now, any question, like last minute question on lab 2 before they due, or like if you have any question on lab 3? Yes.
No, that's why I put it back down because I thought about it.
I mean, any question is fine, really.
I guess like for some of my control stuff, I literally did it in like a small combinational block, which then gets represented in my diagram. It's just a block that has all the inputs and all the outputs. So would you guys take points off for that? Because I'm not gonna do like.
That should be okay.
That should be fine.
Yeah, that should be fine. I mean, because in theory and actually in practice, whatever goes into your core, as long as it's applied by the ISA, is okay. Because the microarchitecture that goes inside the core will not, I mean, as long as it goes along with the ISA and you produce the correct output, that's okay. The trade-off would be like you have more complex design, you spend more area, or you have like a longer critical path. So your design be say slower, for example. So it might affect later labs when you have extra credit on like how fast your core is performing comparing to other students. But yeah, it's all up to you for like what goes into that. You can have like a wrapper modules that takes some particular wires and do some combinational logic on that to make things simpler for your design. Any other questions? Yeah.
Can you explain what you meant by people's PC being off before the last instruction? Are you saying that it was off after they executed the SWI or immediately before the SWI was executed?
Xiao, can you help with that?
So the PC is loaded into a, the halter is loaded into a register. So in other words, it's gonna halt the cycle after it is done. So as long as you increment the PC correctly at the end of every step, you should see the correct result.
Well, right, but when you have a SWI 10, because you're halting, the PC doesn't matter anymore. So whether or not we increment it,
dump is gonna matter. So when we're grading.
Well, yeah, but it should be undefined. I mean, like.
Well, technically, you should move forward, right? Because the spec says that PC should always go to the increment next one. Or suppose if the SWI was actually a no-op. For example, you put swipe 9 instead of swipe 10, right? You will move on forward instead of trapping. So that would be the expected behavior.
But I mean, the default value for a SWI is to go to like what 0x8. So and where does it say, for like at least for lab 1, where did it say that we had to increment the SWI? We had to increment the PC after a SWI, because that particular part of SWI is completely undefined, except for what we're being told to do.
Well,
I think we defined in the first lab handout what to do in SWI specifically. So we call it SWI just because it's a system instruction as such, but it's not SWI as per ARM specification. I think we made that clear in the first lab handout, right?
Yeah, well, right, so it's not an ARM specification SWI, it's your specification SWI, and your specification does not define what PC should be after that.
I think we just define it as increment.
We define it should be
well, you're saying it makes sense that it should be that, but you didn't define it. Like, I don't think the lab handout actually says. It does.
Yeah, it does define
it. Alright. Any other questions from lab 1 and lab 2?
Yeah, just to be totally clear, we don't have to do like post-incrementing or pre-incrementing for memory, correct? Or for like load storage.
That's correct.
Yep.
For synthesis, once you run it through Design Compiler, as long as you don't get any like inferred latches, it's okay, because I got a bunch of like, so my design works, but I got a bunch of signals that say that at some point some net doesn't drive some other net, and I'm wondering if that's because later it's optimized or something.
Most likely, yes.
So it's okay if I get those kinds of errors?
Right? Yes, those errors are fine.
So if the synthesis completes Does that mean it's okay?
If the synthesis completes without
Without-
errors, warnings are right.
Warnings are okay, but if you have errors after synthesis, that you should look at the errors and see what's happening there.
Okay.
Yep.
Would you take off points for inferred latches?
I don't think so.
For this lab, we didn't specify. For next lab, will be more important.
Yeah.
But it is very hard to get a design working correctly with inferred latches, because normally it means it is doing something you are not meant to be doing.
So check your results like carefully, because that might be something wrong or like weird numbers afterward when you have those warnings. So be careful with that. Also, there's one issue with the design compiler about them crashing in a non-deterministic way. And also somebody posted on Piazza, and we actually experienced that with our Lotus simulator too. So just we are trying to figure out what's happening to the design compiler. It might be from,
So someone posted on Piazza today
Mhm.
that you can actually change the design compiler to be less efficient in terms of area,
Right.
but it gets rid of the error. So
Okay.
It's on Piazza, so if you guys have the same error, just go ahead and change your design compiler to that setting.
Yeah.
Also, mine crashed. Like I ran it, and then when I ran it again, it crashed. But I don't know if this was related or completely unrelated. But I just deleted all the files that it generated.
Okay.
And did
So
a clean
what was
run
the
again,
error
and that
you
fixed
got
it.
from the
Oh, it just crashed.
But I think it's
Died.
not problem.
That
Yeah.
might have been memory as well, because
Oh, okay.
you might have run out of AFS memory. It takes a
Yeah.
lot of memory to.
Okay.
did you run it on AC machines?
Yes.
Because somehow there'll be like some random user use a machine and they have like memory leaks.
Okay.
So yeah, that might happen, or like changing machine might help a little bit. Yes.
So I had the same non-deterministic error in 341.
Uh-huh.
I think it's just something that design compiler just crashes randomly. Well, for terms of grading, will you rerun the grading script if
Yes.
it crashes?
Yeah. So if it crashes, you make sure it's not if it's not from your problem or like your handed, you would make sure it's correct.
Because like the way it crashes, it says like it encountered a fatal error now ending or something like that.
Yeah.
Whereas if you have an error, it usually says error and then it points to it.
Right.
So one of the easiest way of doing it is before you check off, make sure you have like a working run recorded.
Yeah.
So when you're checking off, we can just look it from a log or something like that.
Right. Because when we check you guys off, it's like, well, you get it compiled. That should be okay. And if it crashes while we are testing, we're just gonna rerun the test and make sure that we know what exactly is happening. Oh, and make sure you don't edit the main file.
We'll
Any of
provide
them.
a new version with the suggested changes if it helps.
But there was one of the Canon for lab one. We try to use the make file that we provided to you, and it crashes. So we have to spend like a little bit of time trying to figure out what's happening. Alright. Any other question for lab one and lab two and homework one, and also homework two? Yeah.
Just as an announcement, please make sure you submit in the format that we request in the lab
yeah.
handout, because otherwise it's very hard to grade without that same format.
Say, for example, you put in like the folder lab one / something, or like your Andrew ID again, lab one / something, or something along that line. So, yeah.
Oh.
Make sure it's the same format as what we specify in the handout. Any other announcement?
One last thing, when you're checking off, make sure to bring a printout of your
Of the diagram.
of the diagram.
That would help us a lot. Yes?
The checkoff started next week, right?
Yeah, starting next week.
What if like the diagram is pretty big? Can we just show you the PDF? Because that's how I submitted it online. It's like
Yeah,
if I make it small, it's
PDF
gonna
and
be
use the
unreadable.
monitor in
Yeah.
the lab. That also works.
Okay,
Yeah.
We do want a physical hand-in though.
but it's gonna be unreadable. It's gonna be small.
No, if you can do like a couple of A4 pages together, if that's possible.
Okay.
Poster print.
You can stick it together, that's fine.
Sure. Okay.
Don't do the post-it print though.
Yeah.
Those things.
Well, no, but I mean, like, there's a function
Oh,
in
that-
the Microsoft
yeah.
Print where you can tell it poster print, and it will,
Like,
you tell it how
flip
many
this.
pages you want it to span,
Okay.
and it'll just give you each one individually.
mean, if you really love your design, you could print a poster for it and hang it on your wall or something like that once you're done.
Great.
So, if you have any question about lab 1, lab 2, homework 1, homework 2, you can ask me later, maybe during the break or after class or office hour. Also lab 2, because they were released 2 days ago.
Wednesday night.
Yeah, Wednesday night. And that will be on pipelining. So you spend a lot of time implementing pipelining for ARM architecture. And right now, so these are the important topics that we covered so far. ISA, single cycle microarchitecture, multi-cycle microarchitecture, microprogram, pipelining, and branch prediction. And I assure, like, make sure you know all these 6 topics though, because they will be on exam. And now it's a question and answer. You have any question related to any of the topics that you want me to describe more in detail? For example, if Onur went over any particular topic too fast. Yes.
I guess what's the difference between like micro-coded design and like a multi-cycle, like a pipeline where you're doing, I guess I understand that in a pipeline you're doing multiple things at the same time, but other than that you're just like breaking up the actual instruction execution into multiple cycles.
Okay, so for the micro-coded design, you still see the design as like a single cycle instruction.
From which perspective?
From the programmer perspective. Also
Okay.
the designer. So you for the say pipelining, when you advance an instruction, you increase the CC. You fetch the new instructions.
Yeah, I guess I'm saying apart from doing multiple instructions at the same time through the pipeline.
Yes. So for the microcoded, for example, you stop fetching the new instruction.
Yeah.
So you kind of halt the suppose it. So one of the example is to do the load store multiple instruction arm, where you load multiple things within one instruction. So that one way you can do this, which is what you can do in the extra credit, is to use microprogram in your in your design. And say you are doing pipelining on ARM, so you fetch every cycle you fetch a new instruction. But then once you see this multiple load and store, you do not fetch. You just halt the PC and kind of start the pipeline, and you enable this unit where it starts doing microprogram, microcoded design, where you start looping around this particular instruction. Load, keep loading until you are done with that instruction, and then you re-enable the actual ARM design pipeline and continue with the stream of instructions again.
Okay, so essentially, like the difference is that microcoded design is the worst case pipeline where you're halting at each instruction and you don't fetch until the instruction is completely executed.
I would say don't call that the worst case. It's a trade-off where you have this specialized design that you can put in your core or within the ISA to make some particular instruction more efficient. But it would cost you area and cost, like, internally there'll be some extra cost associated with it.
But you're not running at a different clock rate, so it would still effectively just be stalling the pipeline until you're done.
Yes.
Okay.
But with that in mind, you don't have to say you start the pipeline. You don't have to do like try to fill in the instruction, for example, or like fill in the pipeline. Everything is already filled.
Yeah. Okay.
Yes.
Sort of the same question actually, but is a microprogram design necessarily multi-cycle?
So your question, I want to repeat this for the recording. So your question is multi-program design or
microprogram design necessarily multi-cycle?
Is microprogram design necessarily multi-cycle? Usually yes. I don't think there's any I don't feel like there's a point of doing microprogram design with one cycle. You can execute that within a single cycle anyway, right? But I mean, if you want to implement it, you can probably implement that design. But what would be the benefit?
What would that even mean?
Yes.
Well, like from the ISA perspective, it's multi-cycle, but from the microarchitecture perspective, it's single cycle. So like each micro instruction takes one cycle.
No, but his question is like, what if you have a microprogram design that takes one cycle, which is pretty much, I would say, meaningless because you don't have to do that. I mean, why would you design something like that? Just have like, you would just call it a single cycle, like say, design anyway. So, yes.
So for microcoded, it says the control signals determine the next state.
Yeah.
Can you explain that?
So your question is, can you explain why would the control signal?
Just how it's done.
Okay, so how this microprogram is done?
How next cycle is determined in the microprogram.
Okay, how next cycle? Suppose first thing first, you still advance the clock. So clock is still ticking. So let me use the multiple load and store as an example. You don't fetch the next instruction, so that the pipeline is halted. But then, because the clock is ticking, you have another control signal that control this particular load and store that keep advancing from state 1 to state 2 to state 3. For example, let me draw a diagram. Suppose you want to do a multiple load and store for the multiple load for the instruction arm. And your microprogram design, you can think of it as like a table of states that you cycle through. So the first entry, first column would be the state, and whatever goes in here will be just the index, so that you can loop through in your FSM. And then you have the data path that is capable of actually doing a single load and single store, right? But and each one of these data paths are being controlled by some signals. So say for example for state 0, is the initialization state where you decode this particular load. So the control signal would be first like halt the PC. So you assert a signal to halt the PC. And then you assert another signal to advance this state internally. Which pretty much just say whatever the state is from this state, jump to this the second state, which is 001. And in this the next state, what would you do? The first thing you would do is you try to load the data to some location in from get the data from some location in the memory and load the data to say a register. So in here you perform one load. And what you would assert in the control signal is whatever you have to assert for a single cycle load instruction, that connects to the main memory, so that you can load one particular memory address into the register. So this, what would you do here to assert a load instruction in memory? And then the next thing you would do is to go to the next state. So for this case, what you would want to do is to check whether you're done loading or not. If it's not done, you cycle through the same state, then load the next instruction, move the index that point to the particular location in the memory to the next location, so you can load the next entry, and say, suppose the next state will be the done state, which is the third one. What would you do here is to unhalt the PC, and then disable this state and go back. Make sure whatever goes into it go back to state 0. And then you're done. Once you unhalt the PC advanced, it fetch the next instructions. You finish performing all these multiple load instructions for the ARM, so that one single ARM load multiple load store instructions. So this is one way you can do the microprogram, microcoded instructions within single cycle design. Any other questions? If you have any other questions, feel free to ask like anytime during this lecture. And what I'm gonna do next is I'm gonna split you guys into multiple groups of 5 and work on some sample problems. Some of them come from previous exams, some of them come from previous homeworks, and this should be really beneficial for you guys so that you can study on the exam and you know like what particular topic that you might want to study more, or that you already forgot about, like previous early lecture, like pipelining or data dependencies. So yeah, why don't you guys just like group into like group of 5 right now? And any questions? So there'll be a bunch of questions I'm gonna ask like after this slide. Any question that each of the group get it right, I'll give like extra 1% on homework 2 as extra credit.
But we can all get them right.
So the whole group will get them.
But it's not a competition, that's what I'm saying.
Oh, so the first group to answer. So try to beat the time a little bit. Otherwise, the grade will load to some degree, because anyone can just like follow what the first group answer, and then you either all get that extra credit or not getting that extra credit.
Yes, but then only the people who are here would get the extra credit.
That is also true, but I mean that holds true even if it's like.
We should all get baseline extra credit.
Yeah.
Right.
Yeah.
Exactly.
Yeah. So let's do that right now, so you guys can practice on like a question.
Yeah, group of 30.
That's a little too big. And that would be like a group of 30 versus a group of like 13 like the remaining students in the class. Okay.
Then we'd have to divide the 1% by 30 as well.
Alright.
I keep trying to change it.
How many people need like a scratch pad? Like
Do we all need to write it down, or can one person?
Just in case you want to use it. I mean, you don't have to write it down.
I mean, we have to see that they got it right.
Yeah. And double check with me when I have like. Alright, do we have? So does.
Julian was like, what about
There are like 6 over here. You want to like literal alone?
Is it a hard limit
with them.
of 5?
You're with them.
So 4.
Yeah.
Is it a hard limit of 5?
Yeah. Alright. Wait. I thought you guys already have 5. He's working with this guy. Yeah, so you're okay. That's the 5 over there. I guess. Okay, 5.
We're 4.
Cool. Hey.
Whoever's in the back, I think that's like a group of 4 in the front here.
Oh no, we're 5 now.
Okay, you guys are 5. Now you're 4.
Yeah, I'm gonna probably, but then I'll ask when they respond to answer the question. That is one of the things. So be mindful.
Sure, Mirage.
Alright, so we have
Are there
so
really
this is
30
group
people?
1, group 2, group 3, 4, and 5.
I'm like, okay, so now I'll put up this is here. This is only the first chapter.
Alright, ready? So the first practice question will be on the ISA, and whoever actually had checked out homework 2 would get some advantage for this.
Nope, I didn't find it.
So this is the optional question in homework 2 relating to the data reuse in the different ISA. The question is you have 2 machines. Both of them are the 3 address machine, but one of them is a memory-to-memory machine. The other one is a load store machine. There are differences between how they perform load and store. The first one, you can read from here. And I'll put this up here, and I'll write out the question over here. Process this information first while I'm getting the questions ready. Alright, and consider these 2 programs.
That's good. I mean, I'm not which is what happened last week. There weren't tables when I left, but I guess people probably like made it small. I don't know. I was fine with static last night. Because the upstairs was downstairs. Well, yesterday upstairs was just wasted CMU students, and the downstairs was hungry CMU students.
in this table.
Are A
What?
addresses?
Yes.
Are A and B addresses?
A and B, they are addresses in the memory location. So you can load and store
Okay, so you have to load them. Okay.
For machine Y, each instruction is encoded in 4 bytes. Does that include the register numbers?
Each,
We just sort of reason.
just assume that each instruction that you use is 4 bytes.
Total.
Total.
Delivery is 4 bytes.
I mean, I just approximately what the stuff is.
And when you load, like when you say load the data, any data from the register with 4 bytes. Alright, then the first group that got the answer, come up here. I'll give you the mic, and you guys.
For the instructions or what? Number of bytes the program?
Yeah, totally fetch from the memory. And that's another mistake that people did in the previous homework. Total instruction, a total memory bandwidth includes both instruction and data.
If data values are 4 bytes, is that memory address or?
No, say you want to load something into the register.
Yeah.
That particular load from the memory would cost you 4 bytes of data transfer.
Okay. So immediates are 4 bytes. What about immediates?
But you have to load immediate. Oh, you're gonna like hardwire the immediate. Like
Well,
say
I mean, for
one.
machine X, you
Yeah, that's fine. That's not loaded. So you won't waste that 4 bytes.
What's the point of the opt M3M1 in machine X?
3 in 1. Immediate. Oh, just so that you can actually perform an operation on immediate. It's a fetching another data from into.
Oh, immediate, got it. Oh.
Yeah.
So we're just getting the number of instructions or the total bandwidth?
Is it the number of bytes
Number of bytes.
transferred?
Transferred. So this includes the instruction. Okay.
Well, yeah, but I mean, you can infer that from like how many memory instructions.
But that's only load and store operations, or if you for machine X, the first one.
Yeah.
If you do 3 memory allocations, that's
Then that would be 3 memory
3 times 4 bytes.
Someone work on my day. No, let's just finish off my day. So we're gonna have the same meeting.
The program.
Let's do it.
Alright. You can do it.
Sick, dude. I just like
It's okay. Oh, I get to speak?
You got to speak. You get to work through the problem.
That's why I told you to go.
Oh, okay.
Wait, shouldn't you check whether it's right first?
Oh yeah, you should probably check what's right. Before I embarrass myself in front of everybody, you should check to see if it's right.
Because then someone else can get it.
No, what I'm gonna say is, if anyone else gets the better solution, because they can kind of like override your solution.
Okay.
Yeah.
Alright, whatever.
So it's like Jeopardy where you can.
Yes.
Whatever.
Yes.
So should I write down, I guess, the program?
Yeah. Get it done before they can recorrect you.
Write it on the board.
So do I just write the answer, or do you want me to say how?
We're through a little bit on how you copy it.
Okay.
People can call me.
Alright, so feel free to correct me and take the points.
Whatever, yeah.
So for machine Y and program B, we're told that it's a load store machine. So that means that we're going to be operating on registers. And before we can do that, we have to put the data into the registers, right? So if we take a look at the program, it's B equals B plus A, right? So first we have to load B and A, which means we do some sort of load instruction. Right? To get B into A, right? Sorry, to get the actual value of A into A. We also have to load B, right? So we have another load instruction here, so that we have both values. Then we can actually compute B plus A, right, and store that into some register B, correct? So yeah, sorry. So then we actually do the addition, and this computes the value of B. And now we should probably store B because we just got it, so we're going to go ahead and store that. The next instruction is B plus A. We already have this newly computed B because we just calculated it and put it in some instructions. And we already have A because we fetched it, so we're going to do the addition to figure out what C is. And now that we have C, we're going to take this C and store it. I'm assuming here that every time we calculate a new value, we're putting it into some sort of register that we can use later. Now we do A minus C. Again, we already have A, and we already have C. So we do some sort of subtract instruction here. And this gives us D. Having D, we can take D and store it into memory. And then the final instruction is D minus C. We already have D, and we already have C. Right, and this is supposed to be A equals D minus C. So we do this instruction, which again is a sub. And finally, we store it back into A's address. It should be an STR. So are we okay with this? All right, cool. No contestants. Now we have to look at the size. Data and instruction size are both 4. So what we first do is just count the number of instructions because those have to be fetched from memory. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 10 times 4. So that's 40 bytes for instructions. But we also have the data instructions that transfer 4 bytes each. Yeah. So we look at the data instructions. 1, 2, 3, 4, 5, 6. 6 times 4 is 24. And we add these, and we get 64 bytes. So what program is this?
YB.
Okay. Yes.
Just stand right next to me. Alright. This was YB. Okay, so for XB, it's really easy because all of the instructions in program B are memory addresses, and machine X just operates on memory. So pretty much every instruction looks about the same because you store into a memory location, and then you have 2 other memory locations that you operate on. And since each instruction is dependent on the previous instruction, you can't like reorder them in any way. So what I got was pretty much just an add into B. So we can take the 3 address mode and do like a VBA, and then add CBA. Because we don't have any registers, we can't reuse any of these values. We have to reload them every time. And then you can do a sub into D of A minus C, and then you do a sub into A of D minus C. And each of these memory locations is going to be 4 bytes, because that's being transferred, and then each of the instructions, and this one is 7 bytes. So the total I got was 76. For the 4 instructions is
is useless here. So each instruction is just one load and one store, so 4 plus 4, 8 bytes for memory. And each line of code is 4 bytes, so 7 bytes. So memory for each line of instruction is 15 bytes, and basically every line of code is the same. So times 4, 60 bytes for XA.
Table.
So I did machine-wide program A, and for that, each one of the lines is pretty much the same. It's just a load from memory value A, B, C, or D, and then you do the operation, which is an add or subtract, and then you store it back into the memory address, and you're doing the store times. So that's 12 instructions, which is 4 bytes each, and 8 memory operations, which are also 4 bytes each, so that's 80.
Alright, cool. Any other groups want to like challenge this? But I think it's pretty much correct. Okay, cool. So what's the group number? 1. What numbers? So I can keep track of how many points people got. Yeah. And I'll like get your NUID afterwards. Okay, so yeah, that's how. That's why a lot of industries switch to multi-core. Just like have 4 people work on different questions. Okay, yeah, that's a best go. Sorry. My bad.
I'm numb to it. Because Onur does it all the time.
Does what?
Like, you know what I'm talking about? Like, we'll be in a meeting or something, and somebody will say something about, oh, well, I can work on this, and you can work on that. And I'll be like, ah, pipeline, excellent.
Next question. The question is simply, what does this thing do?
Sorry.
Yeah, I got it.
That is really fast.
Yeah.
Right.
Well, I told Onur I understand these way better. Like, well, do you want me to just like say the answer, or like what are you looking for in terms of the answer?
Like explain how you got the answer.
Okay.
As in like come up here and like work the prompt through in the board, so that if it's wrong, people like other groups can like kind of pick you up and start from there. Okay.
Wait,
Still
what
in the
happened?
pipeline.
So we got.
Okay.
Wait, does he get it?
I guess.
They also got it.
Oh.
That group too.
Well,
I guess you get to go first.
yeah. So I guess should I talk about it? Or should
Yeah,
I...
talk about that. You can say the answer first in case it's wrong and
Alright.
other groups correct
Well,
it.
it's going to determine if there's an even or an odd number of ones in X.
That's really fast answer, but yes, it's correct.
Yes.
Can you show how you got that answer?
Right. So if you look at this portion of it, well, whenever you're doing a subtract one and then looping around, like that almost always means that you're doing a pop count. So like I know that there's some type of like you're basically iterating, and for every one that you have in your initial value, it's going to iterate again. And then this is just going to keep looping, switching between true and false until the output happens. So, yeah. I don't know how much like detail to go into.
Okay. I think that's enough. Yeah. Alright. I guess in case people are looking at previous exam, previous homework, can you guys close the laptop?
I'm not looking at the last exams.
That would call them off if they start opening things like that looks like anything, or like PDF files.
No copy in my lab.
Yeah. Alright. This will be a question on pipelining. So, what are the three? Well, by the way, what's your group number?
2.
Alright. I saw hands over there. Did you guys?
So there's the data dependencies.
Yeah.
And is that control flow dependencies?
Mm-hmm.
And the third
It's like, oh, you're right.
It starts out empty.
I guess it could be the third reason, but like that's another reason. That's control dependency.
That's control.
Memory stalling? Yes. I mean, you can call that resource contention.
Oh, resource contention.
Yeah. So you get 2/3, you get 1/3 of that.
Deal. Alright, and what are the costs of all these three dependencies?
Right after read, right after write, right after read.
Like, give me an example, like a code snippet here.
One is to like draw the code.
Got it? You can take that too.
Alright.
I might just like heal over on my way to the board. Okay.
So read after write.
Read after. You're on my stage. Read after write. But then you have like one, and you're copying it with
So you have to
reading. This is reading from R1 after you've written the R1. That's the read after write. And then what's right after write? So right after write doesn't matter as much. It's just if you write the R1 and then you write the R1 again. Nobody really cares. That's cool. And then right after read is you read from R1 or whatever R you're doing. And then you write to it. Again, nobody really cares.
Okay. I don't think you have to like repeatedly say it.
one that really matters.
So you can't like reorder them.
Actually, that's not true.
So it like depends, because you are sharing the reference, it depends. So you have to make sure that you're, for example. Okay, so what he said was this is the only real. The reason that he said it doesn't really matter is because this is the only real one, because it's kind of dataful. You're passing data through this, whereas the other ones are only a limitation of how many registers you have, and where you don't have like a gazillion, you can just continually assign new registers. But these ones you have to be aware of, for example, because let's say you look at what is this right after read. If you're doing some sort of data reordering or reordering instructions in real time, you have to make sure, for example, that this has been read before you overwrite the value. Yes. So yeah.
Like, for example, we have like branch data slot, and you move one instruction ahead of that time. So now they are not it's possible that they're not running in the sequential order anymore. You have to be careful about this two dependencies. And later on in the class, we're gonna cover what we call out order execution, which means we are not gonna execute instruction in the sequential order anymore. Because sometimes when you do that, you can sometimes stop the pipeline. But if you can reorder these instructions and then let some other later instructions where the data already arrived in default order executed first, you can run into some of these dependencies issue, and we'll go over how to make sure we don't have these dependencies issues. Right, and give me 3 ways to eliminate flow dependencies. Yes.
Data forwarding.
Yes.
Bubbling, like stall bubbling.
Yes.
And
you went through about like 5 techniques especially.
Do something else.
I think it's pretty universal. Can you like elaborate? Yeah.
You can use instructions around these to put non-dependent instructions in between.
Yes, you can do things out of order. Yeah, actually, go ahead. Like finish off.
I had a question as to like what do you can't like really eliminate the dependence. You can only wait until it doesn't affect your pipeline really. Right? Because the dependence is still there.
Okay, what you said is true. That's the dependence still there. So you have to store that particular instruction until either that or you can do data forwarding, where you forward the data. The dependence is still there, but you can execute that particular instruction.
Well, yeah, but if you're doing superscalar, then that doesn't necessarily work.
Yeah.
Fine-grained multi-threading?
Yes, that also works. Okay.
Cool. We good? For the previous one.
Yes. Yes.
So we get 2/5 of a point.
And you guys do, yeah.
Wait. We're group 1. We got the 1 point.
Where's some other group?
We'll get group 2.
Pretty sure you're right.
Oh.
And
Pick a number.
oh, wait, pick a number.
We're before.
I'm not happy if I found a grade in the class. I'm going to bring up this
We'll be
class and say,
I think I added up all one.
We'll be 4. We need our 2/5.
Oh, okay.
It's okay. Yeah, we're 4.
Isn't? Oh, you guys.
We'll be 4.
Right. And this will be a problem about branch prediction. Look at this code snippet, and I'll write down the problem that I want you guys to do. In particular, look at the outer loop and the inner branches. Like, can you guys go for the top? Like, back there.
last time predictor per branch or just a random register that has one bit somewhere?
I think you have to know the definition. I'm not gonna hit you on that, but yeah.
Oh no, but there's like different implementations that you can take.
You look at what you branch last time.
No, I mean I get that, but you can have, for example, a table where you
have a global branch.
Global one
you
bit.
have a per branch.
Yeah.
You talked about the global
prediction.
branch.
Global one bit. You only have one bit to check.
And the 2-bit saturating counter, how does the jumping work? Because there was one where you go from 1 1 to 1 0 to 0 0, and there was one where you go 1 1 1 0 0 1 0 0.
One of those was a saturating counter, and one of them was a different kind of counter.
I think so. So this one is a saturating counter.
Okay.
Where there's like a weak, like weak taken.
Well, yeah, I mean, but those state names were assigned in both of them. It was just the flow that was different.
It's saturated. That's a good.
Yeah, saturated. Yeah.
Okay.
Yeah.
Is it fair to assume that there's no interference between the mapping of them? And are we going to include the program counter into the mapping?
Oh no, there's no program counter involved.
Okay.
And this is the accuracy of all of the branches total.
Yes. Like accuracy of the branch when you start executing from this line until you hit this line.
Right.
Which is actually after you
yes, boundary conditions.
Yes.
So like, what is it initially set to?
Think about it. But that goes into the answer.
Well, I mean, so if this whole thing is in its bigger loop,
It's initially set to unknown.
it's initially set to unknown.
Like don't care. X value.
Well, then is it gonna guess? Is it always gonna get it wrong?
It's gonna get it always wrong.
Okay.
How many bits in the global history are we using for this design?
1 bit, 2 bits.
Okay.
Yes.
Are you looking for the accuracy for each individual branch?
No, it's like, what's the prediction accuracy once you finish running this code? How many times would it get it right?
Are you having 2 different predictors for the different branches?
No, everything shared the same predictor.
Oh, everything is in one, so there's no global.
No. Everything in here shares one like global predictor.
Oh,
Yeah.
Oh, okay. I thought it was like the global history that maps into the.
No, just everything. What if everything shared is
Shares one thing.
Oh.
Yeah, so that they can use it to let us out what have we get, what should they be.
Is it 1 bit or 2?
What they get.
Oh.
Yeah, this is 1 bit.
Like this should be done by
Wait, is going into the for loop considered taking or not taking?
Going into the for loop is definitely taking.
Doesn't it depend how you write the for loop? You can either do your conditional branch at the bottom or on top.
No, the conditional branch is always at the bottom, because otherwise you have an additional branch.
So could we try a solution?
Sure.
Yeah, you're right. So, is the for considered taken or not taken?
Oh, okay. So the for taken would be like looping. Yep.
And then for the ifs, taken is the first one or the second one? Oh, taken. Here. Missed that.
modular, every 4 times it repeats. Okay, so because it's modular arithmetic here, every time you get a mod, the mod 4 means that every 4 times it's going to be the same thing. So 0 mod 4 is 0, 4 mod 4 is 0, 8 mod 4 is 0, and for 2 is every 2 times. So the first time we go through these if statements, it's going to be 0, and both of them are going to be taken. So it's taken, and then the next time it's going to be 1, and neither of them are going to be taken. So it's not taken, not taken, and when you change from the taken to the not taken in a 1-bit, you get a missed branch prediction change in there.
You're missing the takens for it.
Right, because those happen every time.
Yeah.
Shit. Alright, I'll have.
Feel free to come up.
So I forgot that you take it.
That's what I was thinking.
But they're all taken.
All right, I have an answer.
Let's do it.
Alright, so the loop branch is going to be taken every time. This is only taken a quarter of the time, and since this always comes after a loop branch, which is always taken, then this will be predicted correctly 25% of the time. This one is taken half the time, but it's like it'll have the same branch as this one 75% of the time. And by that I mean if this one's taken, then this one will be taken. If this one's not taken, in 2 of the cases where I is 1 or 3, then this will also not be taken, so this will be still correct. The only time that this will be mispredicted is if I is 2 or if I mod 4 is 2, in which case this will not be taken and this will be taken. So this will be 75% of the time. And then the loop, which comes after this branch, this is taken every other time, and the loop is taken every time, so 50% of the time the loop will be correct. So that's 50%, 75%, 25% for the 3 different types of branches here. And each of them happens 1,000 times. So you can just average them and say that the branches will be predicted correctly 50% of the time for A.
I think it's actually 33.
So minus the first branch.
Well, yeah, minus the first, but since it's 1,000, it would be off by max like 0.1%. So I'm happy with that prediction.
And you guys have an answer for 2?
We start off with taken, taken. This is the repeating 12 branch pattern for 4 loops, I think. Yeah. And so, if we assume this one starts thinking that it's going to be weakly not taken, then this one is incorrect, but then it's weakly taken, so this one's correct. Then it's strongly taken, so then both of these fail because it becomes weakly taken, or weakly taken. This one's strongly taken, this one's weakly taken. And then this one is weakly not taken, which means this one also fails. Then another weakly taken, so this one fails. Another weakly not taken, so this one fails. And then here we have a weakly taken, so that succeeds. So this is now strongly taken, so both of these fail. And it's now strongly not taken, so this one fails. And we're back to weakly taken being, or weakly not taken being correct here. So this pattern will keep repeating, which is crap, that's only 3 out of 12. That's different from what I had. Okay, well, I'm going to go with this answer, which is 25%, I think.
Okay, roughly, yeah.
Roughly.
I mean, in the actual exam, don't forget when you enter the loop and when you
so
exit
entering
the
the
loop.
loop the first time, this will be a 1, so that's an extra 1 out of 1,000.
Yeah.
The final loop
Lot of
will be not taken, which
3,000.
would be another correct, which is an extra 2 out of 1,000.
Sure.
So it's 25 point.
Even anyone can do the number. It's like three extra.
Yeah, it's close, but it's around 1/4.
Right.
So 24.9%.
Something along that line. Yes. In the exam, make sure you take into account both when you enter the loop and when you exit the loop and get the correct answer. Or if you want to approximate, say you approximate it because that's this time when you enter the loop and how many times in extra that would be correct or incorrect.
Can you give us an idea of what the point, like, result would be if we forgot to handle that case?
That would have to depend on the rubric, but I'm not gonna say it's gonna be a lot.
I
I have a question about this. So when we have the for loop conditional,
Yes.
If we go back into the loop, is that counted as taken or not taken?
It's counted as taken.
Okay.
And like during the exam, if you have any like, questions like that, like does it count as taken? Taken when you look back, just raise your hand and ask if it's something.
I mean, it should always be taken, shouldn't it?
It is.
Unless you have like 2 branches in your for loop doing something.
Yeah. I'm just saying like, oh, if you're unclear about things like that, which is more minor details, if you ask. Right. And using the same code, but what if we use a global and local creator?
How many bits?
2 bits for the global. And then 2 bits for every entry in the local counter.
Wait. I don't, can I ask questions about a global predictor in general?
Yeah.
So a global predictor, that with 2 bits, that means that there's 4 like PC suffixes or whatever, however, that you're keeping track of independently. So are we guaranteed that each of the 3 branches here are in separate buckets?
No, they share the global. They would share the global entry.
What is the branch prediction? Goodness. If it's a global branch predictor.
Do we get a point for answering? Do we get a point for answering B?
Yes.
But it doesn't matter, it's points.
Good volume.
So we're going to say it's 25% because it should technically be the same as the saturating predictor.
Why is that?
Because if they're all in the same entry in the global table, then it's a 2-bit table saturating thing.
I think he missed.
Yeah, I think
That's where you have the bits
Right.
and you shift them.
He's like, that's the lookup thing. They used to look up the independent buckets, right?
right. They look up independent.
He
Like,
didn't understand your
local.
question when you asked it.
Oh.
So you understood it as they all fall in the same bucket, so it would be the same thing. But I
Right.
think that's what
But they're so essentially.
So each of the local branches have their one bucket. Yes.
Okay.
Yeah.
That's different.
Okay, so we have 3 types of branches, so they can be represented by the 2 bits. And the first one takes
So basically, this is a saturating branch predictor, except it's like having 3 independent branch predictors for each of the branches. So we can think about them independently. For the for loop, since it's taken every time, it'll always be strongly taken, except for the first 2 times, so that's 99.8% accuracy. Well, the first and the last time, so that's twice that it would fail, 99.8%. This one will always be either strongly or weakly not taken, which means that it will be mispredicted 25% of the, or it'll be mispredicted 25% of the time, or predicted correctly 75% of the time. And then this one, depending on how you enter the situation, I'll assume that you're starting out with no knowledge, in which case it'll jump back and forth between weakly taken and not taken, in which case it will always be incorrect. But we don't necessarily know that that's the case, because if the predictor had been trained previously, in a worst case scenario, it could have been, or in a best case scenario, it could have been strongly taken, in which case then on the first iteration it's taken again, it's still strongly taken, and it would go back and forth between strongly and weakly taken, and it would be correct 50% of the time. But the worst case is that it would be predicted 0% of the time. So 0%, 99.8%, and 75%. So on average, that's 7/12.
It's okay. I
minus a
mean,
little bit.
you
Yes.
got the number roughly correct, yeah.
Yeah.
So on the test, I guess here did we just assume that they're in separate buckets?
No, I asked that.
Okay, because what I was gonna say is you don't actually have to, because so you know the actual pattern that this executes in, right? And it's some sort of repeated pattern, and that's what the actual thing that you do is what gets shifted into the global table. So knowing that pattern, you can actually figure out whether they fall into different buckets or they have an interference pattern, which you would have to do first, right?
But that's given you know the pattern.
But you do, because
no, but like in general, when you design a branch predictor, because you don't always know the pattern, you pretty much try to guess for the common cases.
But I thought that it was, you have this kind of register that you shift in what you're actually doing, and you use that register to map to a table that has the local, right?
Yeah.
I'm saying that the assumption that they're all in different buckets can be verified because you know what pattern this code runs in.
That is true. Yeah. Yes.
Okay.
I
That's what
thought you
was
meant
making
like
sure.
in general, if you don't know the code.
Oh no. I was just making sure because like in the test we wouldn't be able to assume. We would have to figure that out.
Oh yeah.
To figure out whether they like they have an interference pattern.
Yeah, there's no. You can assume there's no interference between buckets. Otherwise,
Oh, you can.
you can assume. Oh, if you have questions, just ask in the exam.
Okay. But yeah, I was just saying you don't have to.
Because if we don't specify anything in the exam, pretty much you can assume that there's no interference.
But
between
but there is fixed.
that
This-
can.
This code.
Yes.
Okay.
Alright, and the last question will be on the branch delay slot. This one should be pretty easy. Suppose you have 5-stage pipeline. Fetch equal execute memory access and write back. How many delay slots you would need? Yes.
5.
Why?
Because you need a delay spot for each spot in your pipeline, such that.
No, but it's a branch delay slot.
So you only need as much to get to the execute stage, right?
Okay, how many?
You only need enough to get to the execute stage. So
Yes,
that's
which
like,
is number.
Fetch, decode, execute. So
Yes. And next we go down to
What if your branch address is coming from memory access? What if your branch address comes from memory access?
it says it's resolved in the execute stage.
Yeah. So, and what's the number of delay slots?
What do you?
That's the question. Okay. I have another question here. What if you can modify anything in the pipeline? What can you do to reduce this number?
But
I think you can like.
Yeah, I think.
You read it before I like.
Yeah.
Okay. That's fine.
Go for
I
it.
mean, it's just the same thing. You're just trying to move it earlier.
Right, exactly.
So that you can resolve whatever you can in an earlier stage and then reduce that.
I'll just like split into half for you guys. Yeah. But you can resolve it earlier by moving this particular computation into the decode state.
Yeah.
So that the delay slot becomes 1. It's easier to shift anything afterward into that delay slot.
But that always assumes that any dependencies that you have
You
are
have to-
resolved in
yeah.
advance. So if you have a dependency that needs to be executed and you're trying, and that's coming right before the branch,
Right.
then you can't really do
Right,
anything.
so
about it.
anything that fills into that delay slot, you have to make sure all the dependencies is still intact and not, you don't run like via sequential orders.
We should share that half point.
Yeah, so we got that.
I think we should
Wait,
both
we,
get.
but we get a half point too. We get a 1 point, right?
Yeah.
Yeah, they got an additional.
Yeah.
Right. Actually, that's all the practice question I have. And actually, those are questions that come from either the exam or the homework, as I say. So you can expect that similarity in the exam question with a lot more number of questions. That's all I have. Anyone else have any questions about like the materials we have been over in the past 4 weeks? These are the topics. Yeah.
I guess this is more of a personal question, but from your experience, how much does he actually bring in from the papers into the exam?
How much did I
I assume
bring in?
you guys have taken the course.
Yeah, I didn't take this class with Onur, so maybe
Oh,
I
okay.
should have a better answer.
I would say it's very important to understand the papers, because while he wouldn't be like, okay, in this paper, what did he mean by this technique or something, but his questions focus more on applications, and a lot of times you may need the understanding from the paper to actually do the questions completely.
Okay, cool.
And I have a quick question about that. Like, would it be useful if I kind of distill all the papers that you've been over so far and like cover that in one of the lab section? Okay, I'll manage that maybe in the next, not next week, but like next 2 weeks, and I'll cover for you guys for that week, and I'll like present the papers that Onur's been putting in the required reading sections, so that is, and that should be about right before the midterm exam too. That should help a lot.
Okay.
Also, I realized that sometimes Onur mentioned about like different machines that use different particular techniques. I'm gonna just do that and kind of make it easier for you guys to like say understand what does each machine do. So I guess I'll mark the next letter on that. Right. Any other questions?
Yeah, Rachata. Say something really quickly.
Yeah, sure.
So you guys should be turning in lab 2 today or before. Just make sure you get rid of any like debug or print statements because our grading script has a timeout, and if you have a lot of print statements on the longer test, it's gonna time out and automatically fail you. So we have to go back and find those, which is a lot of work for us. So try to get rid of those statements. Don't worry about it now. We were just talking about this and stuff. Cool.
Okay, I guess that's all I have for today. If you have any other questions, feel free to post it on Piazza, email us at 447 instructor, or come to office hour. Alright, thank you.
Oh, do you want to take our Andrew IDs for?
Yeah.
Yeah,
no, Andrew ID.
I
Yeah.
can do that. So if you can all just. So. Actually, why don't you just write it on a piece of paper and give me the team name with team number with.
Turns out if people had
So that's why.
Sorry?
That's why I think
Some. It's not even. It means we do have to go back and do it.
Okay.
So that's one thing I have to do. The other is I do want to talk about like the stuff I was posting about today. So
I mean, I thought you guys would do it.
yeah, I'm just asking.
Okay. Yeah.
Like if one of them stands out.
It's 4:30 or 5.
Shaw said it is okay to do 4:30. I mean, up to you guys. I mean,
It works for
I don't
me
have
whenever.
PPD.
I do work. And
Comment out any print statement.
No. It should
That's really
the
all I
output
do.
should just be what format is required in the end, like the R number. That's all that we should. Yeah.
Okay, so I mean, like,
Yeah, but you were given that. This is so hasn't.
I think that we were given things.
I think that's it. We can talk about everything else before 4:30.
Yeah, sure.
If you need help making any like slides or whatever, after this weekend I'll have a lot of time.
I think this is okay.
I don't have those.
Most of them are out.
Can you write the group numbers though?
The group note, but those are the points. What is
Yeah, I know.
I'll just take a picture.
I guess it doesn't matter.
Okay. Because then we have to trust you. Honor code. No, it's fine. It just makes that.
200 wrist.
Can I ask a question about the lab?
Ask you some more about the microcoded one.
Barrage.